All right, happy Thursday, Thursday week 3. Gorgeous weather outside. I'm excited about today's lesson because it's something that I've used so many times. And most people, I would say, at least 3/4 of my students use this topic on their final projects. And so this is something that it becomes useful. I've used in so many ways. I'll talk about that later. So we're going to be dealing with two variables tonight. In every case, we're going to talk about two variables that we think might be related to each other, and that's what Lab 3 is going to be about. So we're going to be looking at scatter diagrams. You've probably seen tons of scatter diagrams in your life. And then we're going to talk about a linear correlation coefficient. I'll give you an easier term for that in a minute. And then we're going to talk about whether or not a linear relation exists. And really briefly, we'll talk about correlation and causation. And I'll show you some fun, cute little things on a different website just because I'm silly and I do silly things. And we're going to find a least squares regression line. So that's all the stuff we're going to do tonight. It sounds like a lot. It is and it isn't all at the same time. It won't take a super long time. I'm also going to show you how to do all of this in your calculator, which is even better. Then we're going to scooch on over to Excel and we'll do lab 3 together. And as I said, it really doesn't take a ton of time. It's really mostly about interpreting rather than the doing of the Excel. It's about interpreting what's going on. So that's what we got going on tonight. This is the last of the material that will be on the test. I'm going to say this at the beginning because I know a lot of times people watching the review or watching this Zoom later on don't watch it all the way to the end. On Tuesday, it's not going to be a regular Zoom meeting. There's not going to be any new material presented. Normally, I would do Zoom meeting from 5:30 to 6:30 for office hours. However, I am going to do 6 to 7 office hours because I have a meeting after school on Tuesday next week. So from 6 to 7, we will have office hours via Zoom. No new material is going to be presented. It's just going to be me sitting here and you guys asking me questions. You can pop in or out as you please. You don't have to go. It's completely optional. If you feel you have the material down and you don't need it, you don't have to come. But you feel free to come and ask questions or just sit and listen to other people's questions. So Tuesday next week is just office hours. And when I send out my Sunday email, I'll mention that again. Thursday will be new material, but Tuesday next week is just office hours. All right. Now that we got that down, let us move on. Okay. So we have a little bit of vocabulary. I'm sorry, I had to click out of something. So a response variable. So I'm sure that you recall, maybe you don't recall, back in earlier math, we talked about dependent variables and independent variables. So one of the variables kind of like it will happen whether or not the other variable is there. It's the one that kind of drives the bus. It's the one that's kind of in charge of the whole situation. And so that would be your deep, oh, sorry, that's the other way around. Dependent variable is the one that doesn't happen unless something else causes it to happen. It basically would not exist without the first thing. For example, miles per hour. I am not going to travel any miles if no time goes by. Therefore, the miles would be my dependent variable. It depends on how many hours I've traveled. Um, let me think. I'm trying to think of something that's not time, but it doesn't, it seems like time is all I have. So, like if something is changing, like feet per second, altitude changes feet per second. Once again, feet aren't going to happen unless seconds change. So one of them, and we have some good examples coming later on. I was just trying not to use them. So our dependent variable is the one that depends on the other one happening. So another term for dependent variable is response variable. This one happens in response to the first thing. It's not always going to be clear which one is the response variable, and one doesn't always cause the other one to happen. Sometimes we just have to make a choice. So our explanatory or our predictor variable is the independent variable. Time is going to pass whether or not your car is moving. Time is just going to pass. So the independent variable can happen without the response variable or the dependent variable doing anything. So the independent variable is the one driving the bus. This is the one driving the bus. So it is kind of the one in charge of making the other one happen. And if we don't have, sometimes it's not clear which one of those it is, or if there is one of those, sometimes you just have to make a choice. Um, but for example, if you were going to talk about hours worked, like how many hours I work every day based on how much coffee I drink, maybe I'm going to say that I wouldn't drink coffee if I didn't work so many hours. So this is a real loose relationship there. But I'm saying in that case, the hours I work would be my explanatory or my predictor variable, and how much coffee I drink would be in response to how much I work. Now, it's not the case. I love coffee and I'll always drink coffee whether or not I'm working, but that was just kind of an example. So the scatter diagram, this is the graph that shows that relationship. This is where we put dots on a graph and we can kind of see the relationship every individual data set. So how much coffee I drank versus how many hours on a certain day, those would be 1 point. And it would have my vertical axis and my x-axis. You've seen these. So that would be my scatter diagram or scatter plot. Same thing. All right, let's move on and take a look at things. Cat hair everywhere. All right. So this right here, this is the example I didn't want to give you before. Wanted to wait. So we're going to draw a scatter diagram, or I'm going to show you a scatter diagram for this data right here. We're going to be doing a lot with this data during this unit or this section. So somebody's drilling for rock. Researchers are they're digging, and what they want to find out is how long does it take them to drill 5 feet based on what at the depth at which the drilling begins. So in this case, my explanatory variable, this would be my explanatory or my predictor variable. It is my independent variable because the drilling won't happen if I don't start at a certain depth. Drilling can't happen if I don't start, obviously. And this would be my response variable. So normally time happens, time passes regardless, but in this case, we're talking about drilling 5 feet and how much time it takes to do that. If I don't start drilling at a certain depth, I can't drill 5 feet. So one of them kind of explains how the other one happens. The depth at which I start drilling predicts how much time it's going to take me to drill 5 feet. So supposedly, we don't know yet if there's correlation there. All right. So we're going to take a look at a scatter diagram. Here's a scatter plot. So looking at this scatter plot, what I'm hoping you will notice is that my lower depths, it's not taking quite as long. For the most part, it's not taking quite as long to dig 5 feet, to drill 5 feet. I mean, like take a look at these dots down here. It's taking very little time. It's only taking like 6 minutes to drill 5 feet. Whereas when I'm getting closer to 200 feet, we're closer to 8 minutes. You can see that if I can drew a line through the center of these dots, kind of sort of through the center of these dots, if I drew a line through the center of them, this is not quite the center, but pretty darn close. You can see that I have a positive slope. Thinking about linear equations, I have a positive slope here. As the depth that I start is getting greater, my time to dig is also getting greater. And so this is what I'm hoping you can visualize, is that it has a positive slope. No, the points don't really nicely match my line, but you can just kind of see that that's the trend. Does that make sense? All right. Let me move. Yeah, there we go. Okay. So this other example that I have is about a golf pro. So this golf pro wants to investigate the relationship between club head speed of a golf club, miles per hour, and the distance in yards that the ball travels. So there's other things that can affect this ball. So it could be if I change the club type or the ball type, if it's a different golfer, if there's weather conditions. So what he's trying to do is eliminate the variability that can happen because of different variables acting on my golf club. So he's going to use the same model of club, the same kind of ball, one golfer, the same golfer doing it every time, and then is taking a 70-degree day with no wind. Sounds like a beautiful day. So he's picking the best possible situation, not changing any of those variables so that the only variable is how fast the club head swings and how far the ball goes. So that's what we're going to look at. We are together. We're going to draw our own diagram. If you printed this out, it's perfect. You have the graph that you can draw. So it looks like this. If you didn't print it out, you can just watch and judge because, you know, I'm not artistic. Not that drawing dots on a thing is too artistic, but I'm not great at estimating. All right. So at 100 miles per hour, we're at 257. So we're just going to kind of estimate where they are. 102. I'm going to draw this nice, pretty. 103, 274. 101, 266. 105. 100, 263. A little more up there. 105, 275. All right. Give y'all a moment. And I think that we would all expect as the club head speed is faster, the ball's going to go farther. I think it'd be really weird if it didn't. Um, Also, thinking about other things that could cause it to not, I don't know if they're measuring it at the point that it hits the ground. I don't know if they're measuring roll. I don't know, there's a whole lot of unknowns here. I'm assuming they're talking about it just where it hits the ground, but I don't know. But you can see by looking at this that once again, if I draw a line through basically the center of my data, make it more center. If I draw a line through basically the center of my data, it's pretty close, that it once again has a positive slope. I can see that as my club head speed gets faster, the ball's going to go farther. You don't have to draw that line unless you want to, but I just want you to kind of visualize that positive slope. I want you to visualize that that is increasing, that it's getting larger. My distance is getting larger as my club head speed goes faster. Any questions on scatter plots? I believe that you will be asked to interpret scatter plots in your homework. I can't remember though. All right, move on. Okay, so we're going to talk about different type of relations. So we are specifically dealing with linear relations in this class. If you are somebody that's going to go on to STAT244 to the next class, you may deal with different types of relation, but we are specifically dealing with linear relations here. So in my very first one, an A right here, this is definitely linear. It's actually almost perfectly linear, and it has a positive slope. You can see as my X value gets bigger, my Y value gets bigger. The way that I like to look at it is going uphill from left to right. That's a positive slope. On B, it is also linear, really nice linear, but it is a negative linear. Has a negative slope. As my X values get bigger, my Y values are getting smaller. So this one is still linear, but it is negative. It has a negative slope. And so the one on the bottom left, C, it is not linear at all. It has a good relation. It looks quadratic, actually. I don't know if you've taken Math 65. We do quadratics in 65. Or if you remember Algebra 2 from high school. But this is a nice, beautiful parabola. It definitely has a relation, but it's nonlinear. We don't say things don't have any relation at all. We generally just say it's nonlinear. It does not have a linear relation or no linear relation is present. So letter D, this one looks like a nice cubic regression, but it's still nonlinear. It has a nice cubic nonlinear. So letter E is basically no relation. It's completely scattered. It doesn't take any shape at all. I don't like how patterned they made it, but basically it's just all over the place. It's no relation. But just to be safe, you would just say no linear relation. Even if you think it's no relation at all, just to be safe, just say no linear relation. And that's going to take care of anything, whether there's no relation at all or there's a relation, just not linear. That'll take care of every scenario. Any questions on this so far? Doing good? All right. Okay, I already kind of mentioned this. Some things once if they have a linear relation, they're either positively or negatively associated. You just got to kind of look at the slope, at the trend. If it's trending upward from left to right, it's a positive association. If it's trending downward from left to right, it's going to be a negative association. This positive and negative slope thing. All right. You will never, ever, ever have to calculate this by hand. It is a big, ugly, not so much fun thing to calculate. I'll tell you what it means, and I'll tell you how you would calculate it, but I'm never going to ask you to calculate it. All right. So what we're looking at is a linear correlation coefficient. We also just call it an R value. And yes, you're going to be asked to find the correlation coefficient um, in your homework. But if you're writing something in a free response type of a thing and you just write R value, that's perfectly fine because correlation coefficient is a really big word. It's two words, but it's a lot. It's a mouthful. So what the correlation coefficient tells us is it tells us the strength and the direction of our linear relation. If it has a really strong linear relation, the value is going to be super close to 1. If it has or -1, has a very weak linear relation or no relation at all, it's going to be really close to 0. So if we were finding a population correlation coefficient, we would use the Greek letter rho, which looks like a P, but we are never going to use that in this class. This is the only time you're ever going to see it because we just don't really use it. We always just use the R value. I don't know why. It's just what we do. Okay, so R is the sample correlation coefficient. We're always going to be using R. So you can completely forget that rho exists and just say, okay, it gets the fancy thing again and move on. Here's how you would calculate it if you were calculating it by hand. Don't do it. You would take each x value, subtract the mean of the x values, divide by the standard deviation of the x values, then take the corresponding y value, subtract the mean of the y values, divide by the standard deviation of the y values. Then you're going to multiply the one for the x times the one for the z together. You'll do that with each and every pair of data values, then add them all up, and then divide by n minus 1. Just don't do it. Just look at this and say, okay, that's pretty, and then move on. I've had one student over my years of teaching that was their hand calculated thing on their final project. And I was like, why would you do that? But you do you. If you want to do some crazy math, there's your crazy math. All right, I'm going to show you some examples with the R value, what they look like. Oh, they want me to give you all this first. Hold on. I have a sneeze. Maybe. Oops. Is there a second one? Feels like it might be there, but it's not quite there yet. All right. So our correlation coefficient is always between -1 and 1. If you have a different number, something went wrong. Between -1 and 1, -1 and 1 are allowed, so including the -1 and 1. If it's +1, it's a perfect positive linear relation. If it's -1, it is a perfect negative linear relation. The closer it is to 1, the closer the evidence of the closer the positive association. So the closer to perfect linear it is. Closer to -1, the closer to negative or to linear it is going in the negative direction. I'm not going to ask you to recount these to me, but I am going to ask you to identify, like a multiple choice, identify, like, is this one right here? Does it have, what is, which option is its correlation coefficient. And I will make sure that it's pretty clear. So I would give you, I don't know, well, you'll figure it out. Just talk about it later. Okay, if R is super close to zero, there's little or no evidence of a linear relation. So closer to zero means that there's not a linear relation or not much of a linear relation, but it doesn't mean there's no relation. As I said before, it could be quadratic, could be cubic, could be exponential, could be something else, but it's just not linear. There's no units, the R value, it's just an R value. And what not resistant means right here, not resistant means that it's heavily affected by outliers. So if you have a very unusual data value in your data set, then it's going to pull that R value. It's not resistant. It can be affected, kind of like standard deviation and mean are heavily affected by outliers. So is correlation coefficient. All right. That's all of the words. Now we're going to see some pictures that are going to make it mean a little bit more. Here's my pictures. Okay. And I'm going to change some of these numbers because I don't agree with them. So the first one, absolutely, I agree with. This is a perfect positive linear relationship. As my x goes up one, my y goes up one, and it's perfect and it's positive and it's a nice straight line and it's great. Letter B, this has an R value of about 0.9. This is really very strong. It's a very strong positive linear relation. Now, letter C, it says it's a 0.4, but it is really more like a 0.6. It's stronger than a 0.4. I would still call that a moderate positive linear relation. 0.4, I usually call it like moderately weak. I wouldn't call it, I'm going to give you a rule of thumb in a minute. D is a perfect negative linear relation. Perfectly negative. As my x goes down one, my y goes down one, it's a perfect line. Letter C or letter E, I can't read apparently, is a negative 0.9. So once again, really strong, but it's negative, really strong negative. Once again, this one right here, I also think that this is about negative 0.6. It's possible that like these ones right here are pulling my R value down a little bit, but I'm comfortable calling that about a 0.6. Letter G, this is really close to zero. There's practically no linear relation. In fact, I probably couldn't find one at all. This is a number that's really close to zero. Same thing with H. H is a nice quadratic, but it is definitely not linear. So both of those would be super close to zero. Any questions on the R values here?
Do you get that R value on the TI-84?
Yes, you do, and I'm going to show you how to do it.
Okay, cool, thanks.
You're welcome. Okay, so I'm going to give you my rule of thumb real quick here. So now these are not set in stone. I've said it before that statisticians do not deal in absolutes. And how you rate the R value is going to depend on how important your data is. If I'm building a space shuttle, my R value better be super close to one. It better be like 0.95 or higher. If I'm putting a garden in my backyard, I might think that zero point 0.7 is pretty good, pretty strong. So there's a lot of wiggle room here. However, if you called a 0.3 a strong linear relation, I'd probably mark you down for it. But if you called a 0.85 a strong linear relation, I'm going to say, okay, that's fine. So these are not hard and fast rules. This is just basically what I do. Okay, I'm going to like write them up here on top. So if I have an R value of about, let's say 0.85 to 1 or to like 0.99, because if it was a 1, I'd say it's a perfect linear relation. I'm going to move that thing. Let's move this thing over here. Okay. I'd call this strong. I would call that strong. If it was, and you can even call it like if you're at 0.85, you could say moderately strong. I probably would say moderately strong. If I was about 0.78 to 0.85, I might call that moderately strong.
So when you say the R value, though, that stands for response value.
No,
R value.
it's a correlation coefficient. I don't know that the R really has what it stands for. I have no idea.
Okay.
Yeah, so we just call it an R value. It's the correlation coefficient. So if my correlation coefficient is 0.85 to 0.99, I'm going to call it strong. And I should make this 0.84 because then it's a different number. If I'm anything above 0.78, like to about 8.85, I might say it's moderately strong.
But you'd say that it definitely relates to like that earlier vocabulary that you were introducing us to.
Like today.
Yeah,
So it's talking about how strong the relationship is between your explanatory and your response variable. How strongly are they correlated?
right.
Yeah. Does that answer your question?
Yeah, basically.
Okay. Well,
Yeah.
hopefully
Yeah, I
it'll
guess I'm just trying to figure out how everything relates.
hopefully as we move forward, hopefully as we when we do some examples, it'll help.
Okay.
Okay. I'm hoping. Hope so. Okay. So I might even I might even I'm gonna move this number. I'm gonna move this 0.78. I might even go down to about 0.72. I don't know. It's these, as I said, these are not like these are the rules. It really depends on the day. So if I go below that, so if I would say, um, let's say, I don't know, about zero point 0.6 to about 0.71, I would just call it, I would call it just moderate. There's a moderate, um, what is a word? What is a word between medium and weak? And I can't remember. There's a word I usually use, and for some reason it's not sticking in my brain. It's not weak and it's not strong. It is, what is it? I don't know. I'm going to leave that there. Probably anything below zero point 0.6, probably about 0.35 to about 0.59, caught moderately weak. Anything below zero point 0.3, I would probably call it weak. And then if you get super low, you're going to say there's no linear relation. Probably, I don't know, maybe if I got down to about zero point 0.1, 0 point maybe 1.5, I would say little to little to no linear relation. I don't know why I can't think of the word that I normally use for zero point 0.6 to 0.71. I'd say we can just split the difference and pull some up high and pull some, or you can just say there's a mild, hey, there you go. Mild correlation. That's a good word. That's not the word I normally use, but I'll use it. Reasonable, modest, those aren't bad either. I would take those. I would take those. Temperate. That's a good word. I don't know. There's a word I normally use, and for some reason, no, balance probably wouldn't work. There's a word I just it'll come to me as I'm moving through, it'll come to me. And then I will be like, "Oh, that's it." But yeah, I don't know. I don't know where the word went. It disappeared. So, we're gonna I'm just gonna call it mild right now, and we'll just leave it there. Because I mean, that's kind of in the middle, and it's kind of like how important is it? I will pull it up more towards the strong or pull it more towards the weak or whatever. And we'll see. The word might just roll off my tongue as we're doing examples. We'll see. All right, let's move on. You guys need that for a little bit more? I'll give you a second. Man, my handwriting's really bad tonight. Sorry about that. Okay, moving on. Okay, so I'm gonna I'm gonna kind of condense some things together that I normally don't, that I didn't previously condense together because it all kind of goes together really well. You'll see. Okay. So we're going to determine the linear correlation coefficient of the drilling data. So you're going to need your fancy schmancy calculator. So you're going to need that. And we're going to have to do some programming on it first because much of the time there's some things not programmed in it that need to be. And even if it already is, it's not going to hurt it by reprogramming it. So I'm going to pop over to my calculator. Okay. Everybody have their calculator. I want you to hit second 0. It's going to open up a catalog. If you have a different calculator, it might not do this, but I think all of them do this. And you're just going to scroll down. What we're looking for is diagnostic on. So once again, hit second 0. Second 0 opens up a catalog, and I'm just going to scroll down till I get to diagnostic on. Whoa, I went too far. They're in alphabetical order. Diagnostic on. This is what we want. Once you get to diagnostic on, you're just going to hit enter, and then you're going to hit enter again, and it's going to tell you it's done. Are we all there? If you need me to do it again, let me know. Okay. Now
I
that you,
actually, excuse me, I did get like an error. It said syntax error, but I thought I did it right.
okay, you want to try it again?
Do you
Second.
mind? I'm sorry to bother you.
Oh, no, no, you're not bothering me at all. So hit
Okay.
second catalog. Let's do it again.
Okay, thank you.
When you do second 0, do you get the catalog?
I did.
Okay,
Yeah.
let's scroll down. And you might have just hit enter one too many times or something. It's no big deal. So we'll
Okay.
go down to diagnostic on.
Okay.
Be there.
Okay.
Okay, enter and then enter and see if it works.
Ah, that time we got it.
Okay. Yeah, who knows what happened? These calculators can be finicky at times. No worries at all.
Thank
All
you.
right. Okay. Y'all know the stat button, so we're going to click this stat button. Actually, and then go into our lists. And I would like you to clear. So remember, arrow up till L1 is highlighted, hit clear, enter. And we're also going to clear list 2. So go up until L2 is highlighted and hit clear, enter. We want both of those blank. Once they're both blank, we're going to enter the depth at which drilling begins in L1. We're going to enter the time to drill 5 feet in L2. L1 will be my X values. L2 is my Y values. I'm just going to enter these in. So just put the number in and hit enter.
Excuse me.
Yes.
My calculator doesn't have an L2, it just jumps to L3.
Okay. So somehow yours got deleted. So go ahead and highlight L3
Okay.
and hit second delete. And it should give you a blank. Do you have a blank list?
Yes.
Okay, now go second 2, and that names the new list L2.
Okay, thank you.
You're welcome. It happens. Okay, so I'm going to enter these in. And the thing, if that happens again and you don't remember how to put that in there, you can just use L3. You'll just have to tell it that's what you're using. Because I've had that happen numerous times where I've lost the list and I just don't want to deal with it. Enter in my L2. And I am the typo queen, so afterwards I always try to go through and see if I made any errors. Uh-oh. Somewhere I went wrong because I have too many. I said typo queen here, 5.88, 50,
You missed
5.99.
190 on the left.
Oh, thank you so much. It's always good to have an extra set of eyes. Cool beans. All right. Anybody need more time? Give me a thumbs up when you're good. I see you checking. I see you comparing, Justin. So just give me a thumbs up when you're good. All right, good job. Okay. Once again, we're going to hit stat, the stat button, and arrow over to calc, just like we did before. Where we're going is linreg AX plus B. That's where we're going. The AX plus B, you may have a memory of this long time ago. If you go in your Wayback Machine, does Y equals MX plus B strike a chord in your brain? That's what this is, except for they use A instead of M. So we're just going to run a linear regression. We're going to create a linear function. So I'm going to click on linreg AX plus B. Your X list should be L1. If it is not, do second 1 and it'll put L1 there for you. Your Y list should be L2. If it's not, hit second L2 and it'll put it there for you. Frequency list and store reg EQ should be blank. So I want to see it looking like this. So what this is telling me is that my X values are in the first list and my Y values are in the second list, and it's going to compare them. It's going to create a line that best fits the data, and it is going to find your R value. All right, and hit enter, and this is what I got. Your numbers match mine? All right, so the R value that we found, my correlation coefficient, or R value that I found, is 0.77. So there's a moderately strong linear relation between the two data values. So that's not too bad. I'm going to kind of, you aren't tested on the coefficient of determination. However, I think there is one question or maybe two questions that ask you for it. So this R squared value is called the coefficient of determination. And what it tells me, and this is not something I'm going to ask you, this is not something the homework asks you. I just want to kind of give you an idea of what's going on here. So the coefficient of determination, what it tells you is the percent of the variation in your Y value that can be predicted by the equation that we just found right here. So when I get an equation that best fits my line, remember those lines I was drawing through the scatter plots? So the line I'm drawing through the scatter plots is the line that best fits my data. It doesn't fit it perfect, but it fits it okay. It fits it the best that I possibly can fit it. And this right here, this R squared value pretty much tells me how well does that line fit? How accurate of a prediction can I make using that equation that I come up with? So here, I can about a 60% strength of that equation. So there's about 60% of the variation in the time that it takes to drill 5 feet can be explained by the equation that we come up with. That's basically what's happening here. All right. And you're not going to be tested on that at all. That's actually kind of a higher level stats question, but inevitably, if I don't answer that, then people are going to be like really curious and want to know these things. They're going to be like, I just don't know what to do here. So that's basically what's going on there. All right. So we have the 77. I'm going to move back to the other screen. So we have a 0.77. I would say that that's a pretty moderate correlation, moderately strong, maybe. So with a 59% of the coefficient of determination, I would be able to predict. I would not be super accurate predicting, but if I wanted to predict the time to drill 150 feet, I'd feel comfortable with it. I would not feel comfortable predicting something like 210 feet down. So if it's really close to my data, I might feel somewhat comfortable with a prediction. Okay, so before we move on, I'm going to actually write this equation. We're going to kind of explain what it is a little bit later, but I want to write this equation down because we're here and I don't want to have to type this data into my calculator twice. So we're going to do that right now. So thinking about y equals mx plus b, the m, which is now the a on this, is the slope. It tells you how steep my line is or how much my y value is changing every time my x changes. The b is your y-intercept. So in this equation, this a value right here is my slope, and the b value is my y-intercept. I'm going to write this down on my screen, and then we are going to, okay, I'm going to call that 1, 2. Plus 5.53. Okay. I'm going to move on to my other screen so you can see. So this right here is approximately what my equation is. So if I wanted to predict how long it would take at a certain depth, I would plug it into the x value. So for example, 140. If I wanted to know how long would it take if I began drilling at 140 feet, I would put 140 in for the x and just math it out until I could get my prediction. And as stated before, we have about a 60% of a prediction of an accuracy here, which length of time drilling 5 feet, I don't think we need to be super accurate. This isn't a space shuttle. We're not building a space shuttle. People's lives aren't in danger if it takes me a couple seconds off. So it's not that outrageous. Questions so far? We're going to do another one. All right. I'm going to pop over to the club head speed. So what I want you to do is I want you to put the club head speed into your L1, put the distance into your L2, and find your correlation coefficient. I'm going to use my little calculator, my handheld calculator, and I want you to try this and get a value. If you get stuck, just hold on and we'll until we do it together. Even though I'm doing it in my calculator, you're not going to see me type it in. I'm so much faster on my handheld. Okay, I'll give you a moment. While you're at it, if you're feeling confident, go ahead and write the equation down also. How'd we do? Quite possible if you got a different number that I had a typo, I should check. I mean, it looks accurate, but you just never know. Nope, my numbers look good. So my correlation coefficient is 0.939. I don't think there's anybody's going to say that's not strong. That is definitely a strong linear relation right there. If I look at the R squared value, and I just lost it. The R squared value is at 88%. So that means 88% of the distance in yards would be able to be explained by the variation in the distance of yards could be explained by this equation. So therefore, I would feel pretty confident making I would not make a prediction like 120. I wouldn't say 120 miles per hour. We try not to make predictions too far away from our data. Unless it's a perfect linear relationship, we generally try not to get too far away from our data. But I would probably be pretty comfortable making a prediction at 110 miles per hour. I mean, because that's not too far away from my data, or maybe at 97 miles per hour, but I'm not going to go 120, 130, because it's the further you get away from your data, the more off your equation's going to be. So anything like within the data or slightly above or slightly below, you're pretty good making predictions. Any questions here? Right, let's move on. So this is pretty much the only screen we stay on this, but I am going to jump to a website because it's funny. So if we have observational data, so basically if it's, maybe remember way back when we talked about the experiment where they put batterers into a treatment program. So half of them went to a treatment program and half of them went to community service. So that's an experiment. It's not an observation. Because I am introducing a treatment, it is an experiment, and we can talk about causation. However, when we have a study that is observational, like these last two things we just talked about, we have a study that's observational. We can't say one thing caused the other. We can say something likely caused something, but we can't say for sure that it caused it because it's observational. So the correlation between teenage birth rate and homicide rate since 1993 is 0.9987, but you can't say that higher teenage birth rates cause a higher homicide rate. The data is observational. I'm going to show you a fun website just because it's fun. Tyler Vigan. Okay. This is just this fun little page. So what this page is it's showing two things that are correlated that really don't have anything to do with each other, but they have a strong correlation. This is a real good example of correlation doesn't equal causation. So the popularity of the first name Annabelle correlates with UFO sightings in Maryland. My correlation coefficient is 0.962. I don't think Annabelle's cause UFO sightings. I could be wrong. Let's come down here. The popularity of the starter pack meme correlates with the automotive recalls for issues with airbags. It's R value of 0.93. There's a whole bunch of them about butter too, but I don't think they're on here. I'm going to go down and see here. Associate's degrees awarded in mathematics and statistics correlates with Google searches for a dollar store near me. It's a 0.991. So I guess if there's dollar stores near me, I'm going to have a math degree. Popularity of the first name Theodore correlates with fossil fuel used in Burundi, 0.981. So this is kind of just an example of correlation doesn't equal causation. It's hilarious, and there's a new thing on this where you can look at the AI's explanation of why they're correlated or how one thing caused the other. That I don't know if you guys have seen the XCX or XKCD comics. They're pretty cool, but the ones about literature correlates with robberies in Vermont. And American cheese consumption correlates with Constellation brand stock prices. So eat more cheese, the stock goes up. So this is on some, I will write it down because it's fun and you can look at it and go back. If you want to go check out some of them, there's tons. You can even make some of your own. It's on tylervigan.com if you want to look at them. They will give you a big long list of things to choose from, and then they give you another list of things that are correlated, and you can make your own. It's kind of fun to play with, and there's so many on there. So if you want to just play around, that's where you can go. I really love it and have fun with it. It's like my favorite thing to show you guys here and at the high school. All right. So sometimes there is a lurking variable. This lurking variable is something that we didn't include as an explanatory or response variable, but sometimes it affects both of our variables, so it makes it look like they have a strong relationship. So these lurking variables are out there. They're things that we didn't consider that look like things are. People use this all the time to try to prove their points. It happens a lot. So here's a good example. So as air conditioning bills increase, crime rates also increase. So you think that because of this, if I just turn off my air conditioner, there's not going to be as much crime. But the lurking variable there is air temperature. So both things happen more when the air temperature rises. So this is a really good example of a lurking variable. A lot of times in a lot of things that people study, poverty is a lurking variable. And I've noticed that in so many studies where if you just consider poverty, you can explain correlations between things. It seems to be one of the biggest lurking variables in a lot of studies, but just kind of something to be aware of, especially as you're doing, like when you get to your projects. I'm not saying you can't have lurking variables there, but it's nice if you can recognize them. All right. And I'm not going to ask you about that like in any of the homework or anything, but it's just something to consider. Okay, we're almost done. We have three slides left. All right. We already found the least squared regression line, but I wanted to I should probably just put this slide earlier, but we already found it. The least squared regression line is also called the line of best fit. It is that linear equation that we just found. That's called a least squared regression line. Sometimes we just call it LSRL. It's a least squared regression line or a line of best fit. I usually just call it a regression line. Don't even put the least squares in front of it. I will say run a regression, find the regression line, because I'm lazy. But it gives you the best linear estimate of your data. So you're not, unless you have a perfect linear relationship, you're not going to have a perfect line. But we can get the best we can. We can do the best we can. And that's what we do here. And use your calculator or use Excel. Sometimes we'll estimate them on our own, but don't even worry about it. Use your calculator or use Excel. Both of them can do it nicely for you. And I'm going to show you in the lab in just a minute how you can do it in Excel. All right, I think that that's the last of the new material. Yeah, because we already found these lines. So that's the last of the material for tonight. I would like any questions before we go on to the lab. Any questions on this material? All right. So
Well, are you gonna need to do the graphing function on our calculator?
no, we're not going to do any graphing now.
Okay.
It's a good question though. You will be doing graphing. We're going to graph on Excel though. We're doing that just now. Okay. That's not where we want to be. I don't even know what that was. Okay. Let my grandkids play on my iPad. They put games on there. It's all right. Okay, so here's lab 3. That's what we're getting started right now. I made up data. admitting that. Please don't make up. I mean, I won't know whether you make up data or not, but hopefully you have two variables. And I wanted you to find two variables you think might be correlated. You think they might be related. One of the things that people have used in the past is they said height of 20 NBA players versus how many points they scored in a season. They think that people might score more if they have larger height. We've done height and shoe size. I just have two spouses, husbands and wives' ages. There's this one, there's no response or explanatory. There's no way one thing doesn't cause the age of the other. So sometimes you just have to choose which one's going to be X value and which one's going to be Y value. It's not going to matter. But sports are one of my favorite places to get data. It just is. For final projects, you're going to need to have two variables, so you can start thinking about that. Next week is when I'm going to introduce your final project to you. I will actually send out the paper and all that next week, and we'll talk about it. I want to wait till you get the test out of the way. So probably towards the end of the week, maybe next week, Sunday, or Sunday's not part of next week. You know what I mean? Probably right after the test, because I don't want you to worry about it when the test is happening. So anyway, so I have two variables I think might be correlated. So you're going to talk about your population. My population could be my Facebook friends. What variables are you studying? You don't have to be interested in them. Just tell me what your variables are. My variables are the age of the male spouse and the age of the female spouse. My units of my data are age in years. And when it says, why are you sure your two variables have association? This is a question I want you to answer before you do your scatter plot. I just want you to say why you think they are associated. I think that people tend to marry people near their age. That's what I would put there. I think people with larger shoe sizes are probably taller. I think taller basketball players probably score more points. That's what I'm looking for. And letter E, where'd you get your data? So provide me the name of a website, how you did your data, how you collected it, or a URL is fine. Okay. So the way that we're going to graph this, the value, whatever value you have on the left is going to end up being your X value. Whatever value you have on the right is going to end up being your Y value. Make sure you put your raw data here. And make sure you have 20 set pairs of data. So like here I have, these are each a set. This is a married couple. These two go together. I'm going to highlight all of them. Even though the instructions say to have 50, that you're here as a reward for watching the video or coming to class, you only need to do 20 of each. I highlighted all of them. Now I'm going to insert, and it usually on recommended charts, it'll give you the right one. If it doesn't, you can click on this little picture right here and get a scatter diagram. But recommended charts will usually give you the right one. So I clicked on that. I put this in here. I'll make it bigger so you can see it. Okay. This is really lovely, but we don't quite have it where we want it. So before you, if you're going to make it, if you're going to do anything fancy with it, make sure you do that before you add your axis labels. So if you want to change your colors or whatever you want to do, make sure that you do that before you add the axis titles. That whenever you change things like that, it tends to throw things off. Anything you add to it, it throws it away. All right, my chart title, ages of spouses. And now I need to put, you need to have labels on your X and your Y axis. So over here, add chart element. I need axis titles for primary horizontal, axis title for primary vertical. So this is going to be, remember the left one is the X one. So this is husband's age. And then my vertical is wife's age. So make sure you have all of that. The next thing we're going to add to it is we're going to add a trend line. So watch this, add chart element. Down here is a trend line. I want a linear trend line, but click down here on more trend line options. So what I would like is I want a linear trend line, but I also want to display the equation on the chart, and I want to display the R squared value. So display equation and R squared value. I'm going to move this because I want it over here. I'm also going to make the font bigger so I can read it because I am blind. Not literally, obviously. You can change the color of your writing also if you want to. It doesn't even matter. You can change whatever you want. Okay. Now that I have this, this is everything you need on your graph itself. But we do need to, need to do a little bit of work before we can get to we can actually answer the final question. This gives me the R squared value. I need the R value. So I'm going to go down here. I'm just going to type in R value. And then I'm going to do math right there. Remember when we're telling Excel that we're doing math, you hit the equal sign. The equal sign says, hey, Excel, you need to do some calculations. So I'm going to type in SQRT. I'm doing square root, SQRT, parenthesis. I'm just going to type in that R squared value, 0.8616. And it's going to take the square root of that, and that's going to give me my R value. So one thing you should note is that when you take the square root, it's going to give you positive, whether your trend line has a positive or negative slope. You are just going to have to be aware whether your trend line is positive or negative, whether your slope's positive or negative. Mine's positive because it's going uphill from left to right. If yours is going downhill from left to right, even though the R value is going to be positive, you're going to have to mention in your next piece, your next answer, that it is negative. So right here in this box, I'm going to talk about how good the association is between my two variables. So my R value is 0.928. I have a very strong positive relationship. So that's what I'm going to say in there, that there's a very strong positive relationship between the husband's age and the wife's age. Very strong positive linear relationship because I have an R value of 0.928. So it says to explain, so make sure that you reference that R value. So reference the R value when you're explaining how you know it's a strong relation. All right. So that's all I have. So I need questions now. Anyone? Questions about the lab or anything we did in class while we still have the recording on?
You have a dependent variable. Is it always on one or the other?
Yes, so the one on the left is always going to be your X value and the one on the right is always going to be your Y value. See, mine doesn't really matter which is which because the husband's age doesn't cause the wife's age. But if there's a real clear one is dependent and one is independent, the dependent would go on the left, which goes on the horizontal axis, and then the independent, oh, sorry, other way around. Independent goes on the X, is your X value going on the X axis, and on the left, the dependent is on the right and your vertical axis. Did that answer that or did I confuse it?
No, I think got it.
Okay. I don't know why I say those wrong. All right. Any other questions about the lab or anything else?
Wait, vertical axis is the y-axis, right?
Right.
Always. Yeah.
Yeah.
Okay.
I think you guys got this. But the thing that's going to take the longest is collecting the data. But usually you can find a website. I mean, sometimes I just go on the census website and grab 20 states information about two different things. Just grab two different things for 20 states, and there you go. The census.gov gives you tons of data. Or you can go to like the weather app and you can say wind speed and temperature on 20 different days or something like that. Say, I think probably it's colder when the speed is higher. So, you know, things like that when the wind speed's higher. Whatever. Alrighty. Anything else for while we're recording? I'm going to turn off the recording in a moment for other questions. Okay.